Hello, this is Mrs. Nearing, and in this video we will be going over a few examples of how to use ice charts to solve for the equilibrium constant. And if you want to follow along in your TRO textbook, the place to look at would be chapter 14.6. An ice chart, what is it? It's a problem-solving strategy. It's a way to set up calculations involving equilibrium systems. It can be applied in any equilibrium situation. We'll be using it a lot throughout the next several weeks. You can apply this with acids, with bases, with buffers, with solubility. And in general, we can break down any ice chart problem, basically any equilibrium calculation, into one of two types. Type 1 is solving for K when you're given information about concentration. That's what we're going to be looking at in this video. And then later on, and in a different video, we'll talk about how to solve for concentration when you're given K. So it's basically depends on, what is your unknown and what is the thing that you're given. All right, so we're going to work through two examples here of how to solve for K when you're given some information about concentration. So we've got this chemical equation right here, and we've got some information, and so I'm going to give myself a little more room on the next page to stop and write this out. And if you want to pause the video right now and try this problem on your own first, and then you can check your work, that would be a great idea too. So when I am doing this type of problem, first I want to make sure I have a balanced chemical equation, which I do. And then I'm going to want to write out my equilibrium expression. It looks like I am given some values in concentration, so this is going to be a Kc expression. If I were given pressures in atmospheres, then I would be writing a Kp expression. And it's going to be products over reactants, so my products are, this is methanol, my reactants are carbon monoxide and hydrogen, and then the coefficients become exponents. And then I'm going to set up my ice chart, and what that looks like is I'm just going to kind of sketch out the reaction over here to the side, and then I'm going to write ICE off to the left, and I'm going to do a quick little chart here, and I'm going to start filling in the information that I know. And I'm going to know something about at least some of the reactants or products initially, and something about at least some of the reactants or products at equilibrium. But I'm not going to know everything, right? So this is a way to organize the information that we know, figure out what it is we know and what we're trying to find. So we know that initially the carbon monoxide concentration is 0.500 molar, and the hydrogen gas concentration is 1.00 molar. It is important to stop and pay attention to Sig Figs. And so what this means is in order to get this reaction mixture going, we put in some carbon monoxide and we put in some hydrogen gas. What we did not add was the product. So there's zero product to begin with. So if it's not mentioned as being there initially, that means it starts with a concentration of 0. Okay, and then at equilibrium, so this is going to be an equilibrium value here, the CO concentration is 0.15. So you want to read the question carefully. Sometimes they will tell you how much reactant is present at equilibrium. Sometimes it'll be product. It all depends on which is easiest to measure experimentally. So in this case, I know what my concentration of carbon monoxide is at equilibrium. And at this point, you should have, the information from the question should give you some information about initial and at least one of the equilibrium values. And from that, you'll be able to figure out at least one of the change values. So for carbon monoxide, I know it's initially 0.5 molar, and at the end it's 0.15. So that looks like we have lost 0.35 molar. All right, so that's your next step, is to figure out change for one of them. And then once you know change for one of your reactants or products, then you can figure out all of the change values. Because, and this is really important, the change represents the chemical reaction that's occurring, which means that the change ratios will match your mole ratios. So like in this problem, my mole ratio it's a 1 to 2 to 1 ratio, which means that for every 0.35 moles of carbon monoxide that reacts, I'm going to react twice as many hydrogens. So I'm going to use up 0.7 moles of hydrogen, and then I'm going to make 0.35 moles of methanol. I notice I'm saying moles instead of molarity, but since molarity is moles per liter, the change in molarity is proportional to the change in moles, which is why this whole mole ratio thing works. All right, so find one of the changes. Then once you know one of the changes, you'll be able to fill in the whole change row. And then to find the equilibrium value, ignore that, you just add together the initial and the change. So initial plus change equals equilibrium. So 1 plus negative 0.7 is positive 0.3. Okay, and over here 0 and 0.35 is 0.35. All right, so now I'm going to take these values right here. Since these are my equilibrium values, I'm going to plug them into my equilibrium expression, and make sure just, square what needs to be squared, and you still have to be careful on this last step here. So it's 0.35, and then this is 0.15, and this one over here is 0.30 squared. Make sure you square that, and again, make sure you pay attention to sig figs here. 0.15. I'm just going to plug this in my calculator real quick just to make sure. Yep, if you look at your calculator, you get 25.9259 I'm just going to round this to 26, because if you look at my molarities, they have 2 sig figs in them, so I'm going to round my final answer to 2 sig figs. All right, we're going to look at one more problem that is similar. We've got this chemical equation, and again, if you want to stop at this point and pause the video and try this one on your own, you can pause it and then restart this when you're ready to check your work. Okay, so we've got our balanced chemical equation. My first thing I'm going to do is I'm going to write a K expression. I'm going to write a Kc expression because I'm being given molarities. So it is going to be products over reactants. Coefficients become exponents. If there were any pure solids or liquids in my reaction, I would leave those out, but these are all gases, so I'm going to include them all. And then you're going to set up an ice chart off to the side, and it's kind of up to you. Whoops. But I would highly recommend that you write the coefficients over here so you can keep track of your mole ratio, and also you want to keep track of where that arrow is. Because something I forgot to mention earlier, actually, let's go back to this previous problem, is that the sign on one side of the arrow is going to be opposite the sign on the other side of the arrow. So like in this first example, the reactants were being used up, so they had a negative change. But when reactants are used up, that means products are being made. So the reactants were decreasing, but the products were increasing. So the change on the left, the sign of the change on the left is going to be opposite the sign of the change on the right. Okay, so then I'm going to write down what it is we know. We're given some initial values. Initially, we have this much CH4, 0.115 molar, and then looks like nothing else. So these are 0 to begin with. Then at equilibrium, we've got this much C2H2. So at equilibrium, we know this is 0.035. All right, so this is what I am given. And then everything else we're just going to have to, derive. We're going to calculate everything else. So if we know this one starts at 0 and ends up at 0.035, that was a change of positive 0.035. Okay. Once we know one of the changes, we can use our mole ratio, which in this case is 2 to 1 to 3, to figure out what the other changes are. I'm going to do a little note down here. Okay, 3 times 0.035 is 0.035 times 3 is 0.105. Okay, so if this one increased by 0.035, since it's a 1 to 3 ratio, the hydrogen is going to increase by 3 times as much. So it's going to increase by 0.105. And then over here on this side, it's a 2 to 1 ratio. And since it's on the opposite side of the arrow, the sign's going to be different. So since my products are increasing, my reactants are going to decrease. And they're going to decrease by twice as much as this one over here. So it's going to be negative 0.07. So again, the values in your change row should match this ratio up here. It's 2 to 1 to 3. And then to get equilibrium, you just add up initial plus change. It gives you the equilibrium value. So it's 0.115 minus 0.070. And then if you think about sig figs, the Sig Fig Rule, as you look at how many spots to the right of the decimal the value has, this one goes 3 spots to the right of the decimal, this one goes 3 spots to the right, so your answer should be 3 spots to the right. Over here on this one, we should end up with 0.105. I think technically with sig figs, this actually should have been 0.11. I should have rounded that to 2 sig figs. So either way, it's not going to affect your answer too much. So if you go through and you plug it in to your k expression, you will end up with 0.035 and then 0.105, and that's going to be cubed. And the bottom, it's 0.045, and that's when it's going to be squared. So if you do that, you end up with 0.020 as your k value. If you had stopped and rounded to 0.11, you end up with 0.023 being your k value, and that's fine if you did that. Although it's also fine to wait and round until the end. So general rule of thumb is to wait to round in your sig figs until that last step there. So, all right, those are 2 sample problems. Thanks for watching.